guys, today we're going to learn about sequences. So your objective is to understand additive and multiplicative sequences. And this is page 31. All right, well first let's look at additive relationships. And this actually means adding or subtracting. So put that up there. Now, when we have a sequence or sort of like a pattern, we're going to look from the X to the Y. Don't look sideways, look from top to bottom in this case. How am I getting from 1 to 4? Well, since it got bigger, they would have to be adding or multiplying. And in this case, 1 times 4 would give me 4, but that doesn't work here. 2 times 4 doesn't give me 5. So that helps me know that it's additive. I'm adding something. Well, what would I add to 1 to get 4? Well, I would add 3. So this is plus 3. And let's see if that works here. 2 plus 3 does give me 5. So now I can find this by adding 3. 8 plus 3, 8, 9, 10, 11. That would be 11. And this plus 3, n is just standing for any number that I choose to do. If I just apply the same rule, I would just take whatever number I place in for n and add 3. So this is actually n plus 3. Whatever number I want to substitute in there. So the rule is plus 3, and my expression is n plus 3. So in other words, I just basically take n and stick it with the rule. Okay, now let's look at multiplicative relationships. And again, this could be multiplying or dividing. All right, so now I'm going to look and see, well, how am I getting from 1 to 6? Well, if I think about this, I could say, well, plus 5. 1 plus 5 is 6. But if I try that to the next pair, 2 plus 5 does not give me 12. So that helps me to rule out adding. And since it's getting bigger, that helps me to narrow it to multiplication. So what could I multiply 1 by? Well, 1 times 6 is 6. And 2 times 6 does give me 12. So now I'm confident that the rule is times 6. And so this would be 6 times 6, which would be 36. And so this would be n times 6. Now, you're not always going to use the letter n. Sometimes you could plug in whatever letter you want, like x. So we don't actually use the time sign when we're showing this with a variable like n. We're not going to put n times 6. The better way to show this is to actually put 6 in front and then put the n afterwards. Whenever in algebra, when you have a number next to a variable, it means to multiply. So, and it's just common practice to put the number first and the variable second. So 6n means the same thing as n times 6. So my expression would be 6n. All right, so now let's look at a word problem and we can see if it's additive or multiplicative or what. Okay, Jared is packing his lunch for school. The empty box weighs 5 ounces. Make a table and graph showing the relationship between the items in his lunchbox and the total weight of his lunchbox. All right, so I've already kind of set you up here by putting a table for you, and we have 1 ounce for an item. Well, his empty box, when there's nothing in his lunchbox, it weighs 5 ounces. So no matter what, it's going to at least be 5 ounces. And when he puts 1 ounce of food inside, now it's 6 ounces. Well, what are we doing here? Are we adding 5? Are we multiplying by 6? Well, because his empty box weighs 5 ounces, that means no matter what we put inside the box, we're going to have to add 5 ounces to it for the weight of the box. So this would actually be an additive relationship because we did plus 5 to get here. So I need to continue that pattern. So 2 plus 5, if I have the 5 ounce box plus 2 ounces, that would be 7. And if I have the 5 ounces and then I add 3 ounces of food, that would be 8. So no matter what I'm doing, I'm just adding 5 or adding the weight of the lunchbox to whatever the weight of the items is. So this would just be n plus 8. Okay, so there's my table. Now I need to graph it. So first I need to decide, well, what should the scale be? I look at item weight and it's going 1, 2, 3. So let's just count by ones down here. Put 0, 1, 2, 3, 4, 5, 6, 7, 8. And then on the total weight, well, it's 6, 7, 8. So I can just count by ones too. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Now, if I graph this, remember the item's weight is 1. So when I have only 1 ounce of items in the lunchbox, the total weight is 6. So 1 right here, the total would be 6. And when I have 2 ounces, it's 7, so 2, and then up 7. 3, 8, 3, then up 8. Now what about when I have nothing in the lunchbox? Would it be 0? No, it would be 5. Because when the lunchbox is empty, you still have 5 ounces that the actual box weighs. So we would actually start here. And you could continue. If you put 4 ounces, add 5, you'd get 9. You can see the pattern. Now, we're going to decide if we should connect these or not. And what that means is this continuous data? Meaning, if I put a line here, could this right here be a dot on our graph? Could this be a dot on our graph? Or is the only thing relevant the actual points that I've already put? Well, to determine that, you really just have to look at this value or this label here, item weight. Could you have only whole ounces of items, or could you have something that weighs 1.5 ounces or 3.2 ounces? Well, yeah, you could have part of an ounce. So it would make sense, because I can have part of an ounce and part of an ounce here, that we are going to connect these and put a little star here, and I want you to write continuous. What that means is that every point along this line has value in this graph. Okay, I can have an item that is part of an ounce, so I could have a point like right here on the line. It doesn't just have to be where these whole points were. Okay, all right. So now I'm going to look at the next one, and again, we're going to read the situation and decide how we're going to fill out this chart. Okay. Ashley is selling bracelets for $2 each and donating the profit to charity. Make a table and graph showing the relationship between the number of bracelets sold and the total donation. Okay, so when she sells 1 bracelet, she has $2 that she's able to donate. Well, it's telling me right here that each bracelet is $2. Each, that word right there, is also a clue that it's multiplying or dividing. So that helps me to realize that it is a multiplicative relationship. If 1 bracelet was $2, if I sell 2 bracelets, that would be $4 that I would now have to donate to charity. So this is times 2. So 3 times 2, this would be 6. And this would be n times 2, but remember, I write that as 2n. Okay, now I'm going to fill out my scale. So 0, since it's number of bracelets, we'll just start 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then I could count by 2s if I wanted here, but it's not getting very high, so let's just count by 1s also. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so now let's graph the points that we already have on our chart to start. So we have 1 bracelet, $2. 2 bracelets, $4. 3 bracelets, $6. You can continue the pattern. You can tell that if we had 4 bracelets, it'd be $8. Okay, and if we sold 0 bracelets, well, then we wouldn't have any money to donate. So that could be 0, 0 also. All right, so now we're going to decide, do we connect these or not? Can I sell, if I connect these, that means anything along this line would be relevant. So could I sell part of a bracelet? Am I going to sell just half of a bracelet? No. So I can't sell a part of a bracelet, and so I'm not going to have anything besides 2, 4, 6, 8, 10, etc. of donation amount. Okay? So I actually am not going to connect this here. And this kind of data is called discrete. Meaning each point on this graph is relevant, but in between is not for this case. Okay? All right, guys. So additive, meaning adding or subtracting, and multiplicative, meaning a multiplying or dividing pattern. Keep practicing, and I'll see you next time.